In this video, we will be discussing the oxidation number method for balancing redox reactions. And so this method is really incumbent on you knowing how to assign oxidation numbers to things. If you can't assign oxidation numbers to elements in a compound, it's going to be really hard to do this method. And if that's something you struggle with, I really encourage you to check out the alternative method, the half reaction method, which I will post some details on in the description, and send you over to Tyler DeWitt's channel. He does a really fantastic job of breaking down into the nitty gritty. But for the oxidation number method, it's going to be where we start with the skeleton reaction. Skeleton reaction is real simple. I've got 1 mole of each reactant, and I've got 1 mole of each product. I'm starting with the simplest reaction that I can. And what I'm going to do next is I'm going to assign oxidation numbers to every element in every compound. And I'm going to use those oxidation numbers to identify the change in oxidation number for each element. And what that's going to really help me with is I can identify all sorts of things. I can identify what's oxidized. I can identify what is reduced. I can identify the oxidizing agent. I can identify the reducing agent. So all those kinds of questions that you get asked from time to time in homework problems, quiz questions, exams, that kind of thing, the oxidation numbers tell us all that stuff and tell us really, really quickly. Now, the next step is I need to balance those changes in value. So I look at my reaction, I see, oh, the oxidation requires 3 electrons, the reduction requires 2 electrons. I can't have leftover electrons, so I'm going to use coefficients to balance that out by making sure that every electron that is lost in the oxidation gets gained by reduction. And so that's what step 3 is all about. And in addition, step 3 will also make sure that all of my elements that aren't oxygen and hydrogen get balanced out in the process as well. The 4th step is to balance the charge. Now, oxidation reduction reactions can occur in acidic solution or in basic solution. The beauty of this technique is that the charge is going to be balanced by those ions, hydrogen ions if it's acidic, or hydroxide ions if it's basic. And so one of the other advantages to this technique over the half reaction method is the half reaction method will always start with acid, and then if it's base, you have to do an additional step to convert it into base. With this particular method, it's all done the same way in that 4th step. And then the last step is to balance the oxygen and the hydrogen using water molecules. So let's take a look at a couple of examples. Our first example here, we have perchlorate reacting with chloride to make chlorate ion and chlorine, aqueous chlorine. Now, one thing I want you to notice right off the bat here is that we have a couple of species here that appear to be very similar to each other. The perchlorate and the chlorate are separated by an oxygen. The chloride and the chlorine are separated by charge and by an additional chlorine over here. There's a good chance that whatever happened from a redox standpoint here, this perchlorate is going to impact what happened in the chlorate. The chloride is going to have an impact on what we see in the chlorine. And so as we set up our oxidation numbers, keep in mind that idea. So the oxidation state for the chlorine here is going to be +7. The oxidation state for the oxygen will be -2. The oxidation state for the chloride here is -1. The oxidation state for the chlorine here is +5. And for the oxygen is -2. And the oxidation state for the chlorine here is 0. Now, if you didn't know where those come from, if you struggled with that, go back and look at that oxidation numbers video again. You really can't do this method without having a good handle on those oxidation numbers. So these are our oxidation states. And again, we can see that, okay, the chlorine here did change from 7 to 5. The chloride here did change from -1 to 0. That's probably significant to us. And so if we look, we can see that, okay, I went from +7 to +5. Well, the difference between 7 and 5, that would be a gain of 2 electrons, which would mean that this is a reduction. And for the chloride, I can see that I went from the -1 state to the 0 state. And so to do that, I would have to lose 1 electron. Now, before we go too crazy with coefficients here, one thing that we have to make sure of, are we talking about the same thing? Well, the answer here is no, not quite. There are 2 chlorines here in the products. There's only 1 here in the reactant. So we've got to clean that up a little bit. And so what that means is we need a coefficient of 2 on the chloride to make sure that we have 2 chlorines present here at the same time. And so that means I have 2 chlorines that are going through that conversion. And that means that the total charge is going to be 2 times -1, which would be a total net loss of 2 electrons. Now this is still an oxidation, but why that's important is now when I'm comparing, now I'm getting into that third step, I'm comparing the change of charge that is moving. I can see that this blue reaction gained 2 electrons, and this orange reaction lost 2 electrons. And since the number of electrons gained and lost hasn't changed, we're good from that standpoint. We don't have to do anything further than that. The only thing that is left to do is to evaluate total charge. To evaluate total charge, I got to cut this thing in half and count. I have -1 from the perchlorate. I have 2 -1s from the chlorides, so that's a total charge of -3. And I've got a -1 from the chlorate, but no charge from the chlorine. So a -1 over here. -3 on the reactants is not balanced with -1 on the products. Since this is an acid, I'm going to need to take care of that. And so I'm going to add 2 H pluses to this side. 2 H pluses plus that -3 will turn the charge to -1. That'll balance out those charges. Now to counterbalance that, I have 2 hydrogens over here where I had none over here previously. I'm going to need to have water added to this side. And now, if I put it all together, I would get something that looks a little bit like this, where I've got the perchlorate ion plus 2 hydrogen ions plus the 2 chloride ions yield the chlorate ion, the chlorine, and the water molecule. And if I add it all together, I see I've got 1, 2, 3 chlorines to match up with the 3 chlorines here. I've got 4 oxygens to match up with the 4 oxygens here. And I've got 2 hydrogens to match up with the 2 hydrogens here. So from an atomic standpoint, it's balanced. Now from an ionic standpoint, from a charge standpoint, are we still balanced also? Total charge over here, -1 plus 2 -1s is -3. plus 2 positive ones. Negative 3 plus 2 is negative 1 on this side. And over here, I just have this one negative 1, so negative 1 on this side as well. We've got everything all balanced up, all right here, right now. So that covers us if we were in acid. Now, what would be different if we were in base? All right, so resetting the screen here, we're in exactly the same place we were after step 3. We've fixed our coefficients, we've settled our charges, and now instead of adding hydrogen ions, we would be adding hydroxide ions to balance out the charges. And so if we do that, instead of adding hydrogen ions, which are positively charged over here, we're going to add hydroxide ions, 2 of them in fact, and that will give us a negative 3 charge overall to balance out the charges. Now, from that standpoint, I can take the hydrogens here. I need hydrogens on the other side to counterbalance, so I need to add a water molecule. And if I sum it all together, now I have perchlorate ion plus 2 chloride ions plus a water molecule, making the chlorate ion the chlorine molecule and 2 hydroxides. Now, one of the quickest things that you can do to make sure that you are on the right footing is to just quickly go through and make sure that you've got everything balanced. Not only from an atomic standpoint, but from a charge standpoint as well. So if I did this correctly, I should have negative 3 charge on each side. I've got a negative 1 here and 2 more negative 1s there. That's negative 3. Negative 1 here and 2 more negative 1s there. That's also negative 3. So charges are balanced. Chlorines, again, 1 plus 2, that's 3 here. 1 plus 2, that's 3 over here on the product side. Oxygens, I've got 4 here, plus 1 more is 5. I've got 3 here, plus 2 more is 5. And for the hydrogens, I've got 2 there and 2 there. I'm all set. So this is my balanced equation in base. So the beauty with this particular methodology, again, is in its simplicity. And its simplicity comes from the fact that you can use pretty much the same procedure all the way through up until this very last step, where you change it based upon whether it's in an acid or in a base. So if you want some more examples, please tune in for the next video. I'll also post some other examples of some practice problems that you can do. But until then, have a good day.